Here we have a speed time graph. We now can interpret what's happening to that moving object by looking at this graph. We can see that over the course of the journey time of 10 seconds, the speed of the object did not change. It had a constant speed of 7 meters per second. Now we know the speed was constant over the whole journey. We can then work out the distance gone, or the distance travelled by the object over 10 seconds. And that's done by our equation. The distance gone is equal to the speed multiplied by the time. So distance is going to equal to the speed, which was 7 meters per second, multiplied by the time of the journey, which was 10 seconds. So that's going to give us a distance gone of 70 meters. Now if we look very closely at the speed time graph, we can see a very important thing. The area of the graph, if I can shade that part in here, is numerically equal to the distance gone. We have 10 across multiplied by 7 up, that's the area of a rectangle, and it's going to give us an answer of 70. Area equals 10 times 7 equals 70. So the area of a speed time graph does give us the value of the distance gone. We can summarise it up with this little sentence here. The area of a speed times graph is the same as the distance gone. Let's try another example. Here's the speed time graph of a moving object. We can see that the speed is increasing from 0 to 8 meters per second over a time of 7 seconds. So the speed is increasing throughout the journey. Now if we wanted to find the distance gone in that journey, we'd have to work out first of all the average speed of that journey and then multiply it by the time, because the distance gone is equal to the average speed, V bar, remember the bar across the T stands for average, multiplied by the time of the journey. But what is the average speed? Well, the average speed is found quite easily. It is the starting speed, 0, plus the final speed, 8, and divided by 2. So that's going to give us an answer of 4 meters per second. So the average speed of that journey is 4 meters per second. It's always halfway if we're going between 0 meters per second and 8 meters per second. So the distance gone by that object, according to the formula, would be average speed 4 meters per second multiplied by the time of the journey, which would be 7 seconds, and that's going to give us a distance gone of 28 meters. Now let's use our theory to try and work out the area of that triangle, because what the area of the graph is in this case is a triangle, and the triangle is a base of 7 and a height of 8, and we know that the area of a triangle is equal to 1/2 times the base times the height. So the base is 7 and the height is 8. So therefore we can work out the area of that triangle, and the area works out to be 1/2 multiplied by the base 7 multiplied by the height 8, and it does come out to give us 28. So the area of that triangle, the area under the graph, exactly is equal to the distance gone. So once again we can state our theory that the area under the graph, the area under a speed time graph, a speed time graph, is going to be exactly equal to the distance gone. Let's look at another example. The distance gone by a moving object can be found from the area of the speed time graph. Here's an example here. We have an object speed time graph, and that speed time graph is telling us the story of its motion. We can see that from 0 to 4 seconds the object's accelerated from 0 to 6 meters per second. And for 3 seconds it travelled at a constant speed of 6 meters per second, and finally over the last 3 seconds of its journey its speed decreased from 6 meters per second down to rest at 0 meters per second. Now our job is to work out the area of that speed time graph, because that's going to give us the total distance gone by that object. So it's not a shape we can calculate the area of very easily. So our first big hint is to split that graph up into shapes such as triangles, rectangles, squares, so that we can work out the area a lot easier. So when you see the speed time graph like that, the first thing to do is you can section it off. I can draw a line down here and you can see that I'm going to have a triangle part in here. The area will be a triangle. I can section the second part off and you can see that area under the graph is a rectangle. And you can finally see that the third part of the area is going to form a triangle again. So all I have to do is work out the areas of those three shapes and I've got the total distance gone. But I've got to be organised, so I label the areas. This would be area 1. In fact, that would be the distance gone in the first 4 seconds of that motion. This would be area 2, and that would be the distance gone in the next 3 seconds of this motion. And finally area 3, that would be the final distance travelled from a speed of 6 meters per second down to rest. So there's all shapes that I can know the area of. So for example, the first area 1, the area of that triangle is going to be 1/2 times the base times the height. So that's going to give us 1/2 times the base of the triangle, which is 4, times the height of it, which is 6. So the first area is going to be 1/2 times 4 times 6 is going to be 12. So I know the number is going to be 12, the area is 12, but the distance gone will be 12 metres. What about the second area? Well, the second area is just really a rectangle, and we can just go the length times the height of it. So it's going to be 3 along and it's going to be 6 up. So for the area of the rectangle, it's just really going to be its breadth times its height. Breadth times its height for the rectangle, which is going to equal to 3 multiplied by 6. So that area is going to be equal to 18. So I would know that in the 4 seconds to 7 seconds, the object would travel 18 metres. And finally, the third part of the journey is we have to work out the area of that triangle. And the area of a triangle again is 1/2 times the base times the height. So it's going to equal to 1/2 times the base. And the base this time is going to be 1, 2, 3. So it's going to be 3 units along. Multiplied by the height of the triangle, which is going to be 6. So the area of that last part is going to be 9. So we would know that the area being 9 translates as the distance gone in the last 3 seconds of that journey would be 9 metres. So the total area of that graph is going to be 12 plus 8 plus 9. It's going to be 12 plus 18 plus 9. So that's going to give us a total of 12 plus the 8 is going to give us 20, 30. It's going to give us a total area of 39 units. And that translates as the distance gone is going to be 39 metres. So the distance gone would then be equal to, the total distance gone would be equal to 39 metres. 39 metres. So we've worked out the area of the speed time graph to be 39, and that happens to be the distance gone over the 10 seconds of 39 metres. So we can find one last thing about a speed time graph. We can actually work out the average speed of that object over the 10 seconds, because we know the distance gone and we know the time taken. The average speed over the course of the journey is going to be equal to the distance gone divided by the time. So we're going to have the distance gone to be 39 metres, and we'll divide that by the time of the journey, which is going to be 10 seconds. So that's going to give us an average speed of 3.9 metres per second. So even though the speed of the object changes all over the course of 10 seconds, we now can work out the average speed from that object's speed time graph by calculating the total area under the graph, which gives us the distance gone, and knowing how long the journey lasts for, 10 seconds, we can finally calculate the average speed of that object to be 3.9 meters per second over the whole of its journey.